Okay, so hopefully you can all see my screen and the title slide that says Interactive Theorem Proving and the Lean Theorem Prover. So yeah, please let me know if there's a problem. But thank you. It's an honor and it's a pleasure to be here. I'm very happy to be here and to speak to you. And let me say that I would like to keep this lecture informal. So please don't hesitate to, if you have any questions, please don't hesitate to interrupt me if I'm going too quickly or if anything is unclear, please don't hesitate to ask. But I'd like to start this talk with a quotation. And I'll read it to you, and then I'll ask you if anybody can recognize it and tell me who the author is. So the paper begins, it says, the development of mathematics towards greater precision has led, as is well known, to the formalization of large tracts of it. So one can prove any theorem using nothing but a few
我靠
mechanical rules.
，English 啊，嗯，
The most comprehensive formal systems that have been set up
我靠，你看
hitherto
我修复了，
are the system of Principia Mathematica on the one hand, and the Zermelo-Fraenkel axiom system of set theory on the other. These two systems are so comprehensive that in them, all methods of proof used today in mathematics are formalized, that is, reduced to a few axioms and rules of inference. One might therefore conjecture that these axioms and rules of inference are sufficient to decide any mathematical question that can at all be formally expressed in these systems. So does anybody know who the author of this paragraph is?
Russia?
No. So the author is Kurt Gödel.
Okay.
Yeah, no, Russell, that would be a good guess, but a little bit later, this is Kurt Gödel. Yeah. So then, because the next sentence in the paper is, it will be shown below that this is not the case. So in other words, the paragraph is saying that we now know that almost all mathematics can be formalized. And so much mathematics can be formalized, you might think that everything can be formalized. Every question can be proved. Every question can be cited one way or another in a formal system. And so that's why the paper was so striking, that he showed that the incompleteness theorems show that in any reasonable formal system, there will be undecided statements. And what I want to focus on is not the negative theorem, that, the incompleteness theorem, but actually the positive claim that most ordinary mathematics can be formalized, right? So he says that, these two systems, Principia Mathematica or Zermelo-Fraenkel, are so comprehensive that in them, all methods of proof used today in mathematics are formalized. And so it's interesting that as early as 1931, Gödel is expressing, he's saying, see, it's clear that at least in principle, we can formalize almost all of mathematics. And so what's happened in the last few decades is that this claim in principle has turned into in practice. So the idea is now, with the help of computational proof assistance, we can actually formalize mathematics. And the idea is you sit at the computer working with a computational proof assistant, and what you're trying to do is construct formal axiomatic proofs. And I'll give you a little bit more of a sense later on how it works. But the idea is, if you're successful, that when you're done working with the proof assistant, you have a formal proof that in the memory of the machine. And this is something that can be, extracted, saved in a file, sent to other programs. Other programs can check it. So it's a formal axiomatic proof of the theorem in question. Okay. And so by now, there are a number of systems with substantial mathematical libraries. So I've listed these, I mean, there are many of them out there. These are some of the major ones, and mostly I've focused on ones with substantial libraries for mathematics so that you can formalize mathematics. And these are roughly in historical order. So, Mizar goes, I think, around 1970 and so on. Isabel and Cook are roughly from the 1980s. Later, I'll talk about Lean, which is the most recent. So that's started in around 2013. And then in parentheses, I'll also say a little bit more about this later. I describe the formal axiomatic system that they're based on. So a couple are based on set theory, like Mizar and Metamath. A number of them are based on simple type theory. and some are based on versions of dependent type theory. Okay. Um, and so, by now, a number of important mathematical theorems have been formalized. So things like the prime number theorem and the four-color theorem and the Jordan curve theorem. I can say so. The prime number theorem was one of my first, successes in interactive theorem proving. I did that with some students at Carnegie Mellon in 2004. Since then, there have been a number of other proofs. So John Harrison did it with complex analysis in Hall Light in 2009. More recently, Larry Paulson and then Manuel Eberl formalized it in Isabelle. Let's see, the four-color theorem by Georges Gontier, the Jordan curve theorem by Tom Hales, Gödel's first incompleteness theorem. I think it was first done by Shankar, Natarajan Shankar. But recently, the second incompleteness theorem by Larry Paulson. Dirichlet's theorem on primes in arithmetic progression, I think first by John Harrison. The central limit theorem that I did with, I'm blanking on my co-author's name. So student Luc Serafin and Johannes Hölzel. And recently, the independence of the continuum hypothesis. So in 2008, Larry Paulson proved the consistency of the continuum hypothesis with the axioms of set theory. Recently, Floris van Doorn and Jesse Hahn showed the unprovability of the continuum hypothesis. So they did that in the lean theorem prover. So these are some big name theorems that have been formalized in mathematics. And it's always nice to prove a recognized theorem. It's kind of like conquering a new territory or planting a flag or discovering something new. But really, in a sense, when it comes to formalizing mathematics, what's more important than the individual theorems are the libraries of mathematics that support them. Right. So really a better landmark is the fact that by now, with interactive theorem provers, people have built good mathematical libraries for number theory and real and complex analysis and topology, measure theory and measure theoretic probability, linear algebra, group theory, category theory, dynamical systems. One way I think to characterize it is, by now, somewhere or another, most undergraduate level mathematics has been formalized. So most topics that a student would see in their undergraduate mathematics education, and then some more advanced mathematics. Okay, and there have been some important landmarks over the years. So one important landmark is that in 2012, Georges Gontier and a team of people completed a verification of the Feit-Thompson odd order theorem. So that was done in the Koch theorem prover. And that was notable. The original paper in 1963 ran 255 pages long. So it was a fairly long proof. In Koch, the proof was actually formalized in a constructive, using constructive logic. So it's fully constructive. And to prove the result, the team had to develop a number of libraries for finite group theory, linear algebra, representation theory, and here at the bottom are some statistics. So it's 150,000 lines of formal proof went into it. And I was a member of this project, so I spent a year living in Paris on sabbatical, so 2009, 2010, working on this project. So it was a very exciting time for me. Another nice landmark was Tom Hales's announcement of the verification of the Kepler conjecture in 2014. So the Kepler conjecture has to do with packing spheres into space. So if you imagine trying to pack spheres all the same size into space as densely as possible, you would imagine that you would sort of pack them the way you would kind of layer grapefruits into a crate, or cannonballs, that you pack them in layers of hexagons. And if you pack spheres that way, you fill up a certain percentage of space. In the 1600s, Johannes Kepler stated, he just claimed that this packing was optimal, that there was no way to get a denser packing. And this wasn't proved until 1998 by Tom Hales, and then formally verified in 2014. So again, the project had a team of authors. I think there were like 14 or 15 or so authors on the final paper. Most of the proof was carried out in a system called Hall Light, but parts of it were done in Isabelle. Um, and the proof required not just verifying pen and paper proof, but also verifying formally a number of calculations down to axiomatic primitives. So that took a fair amount of computing power. Um, okay. So again, let me pause. I mean, so far, are there any questions or anything I can clarify?
Excuse
Okay,
me.
then I will go on, but please don't. Yeah.
So for formalizable, do you mean that is that you just mean that approval in some formal system, right?
Yes. So I'll give you a little bit more information over the course of the talk. But the idea is, yes, there's a formal axiomatic system. And what you're doing is entering to the computer a description of the proof in such a way that the computer can fill in all the details and check every step down to the basic axiomatic primitives. So it's really just like a formal proof that you would do on, with pen and paper, where every line has a justification and there's a list of rules and so on, but much, much bigger. So the computer is helping you manage the size and the complexity of a very large proof. Yeah.
Okay.
Any other questions? Okay. Okay. So so let me say a little bit more about it. So what I'd like to do is convince you now that if you're curious about it, it's accessible. Anybody can start playing around with interactive theorem provers. So here I choose a quote from the Jewish Bible, the Old Testament, where when God gives the law to the people, should say, "Who shall go up for us to heaven and bring it into us and make us to hear it that we may do it?" So it's saying that the law isn't up in heaven; it's everybody can access it. So in the same way, formal theorem provers, everybody can access it. So on the slides, if the slides are posted, these are all clickable links. And so, what I will show you is that, if you click, oops, I just lost it. There we go. If you click on the link, here's the web page for Isabelle. And if you see, you can, download it. You can start reading tutorials that will teach you how to use it. So there's a lot of information, and there's the libraries. And you can see there's, let's see, so higher order logic. You can start looking through the libraries. See if I can find some more interesting ones. So here's a little bit of number theory. So, so these are these are roughly the formal text that's entered to the computer, and the computer is then going to use more about it. But so that was just Isabelle, and in a similar way, I talked about the FlySpec project. So that was in a library. Sorry, not the FlySpec, the Feit-Thompson verification. That was in a library called Mathematical Components, based on Cook. And again, you can download it and install it, and there's a book that will teach you the library in the system and how to use it. And another one, there's Metamath. So Metamath is like a assembly language for set theory. It's very low level, but you can, again, you can kind of, explore proofs and click around. So later in the talk, I will tell you about a system called Lean, the Lean Theorem Prover. So that's the project I've been involved with most recently, and it's a very, very wonderful system. But once again, there's a lot of materials there. So they're very nice web pages. Here's the Lean community web pages, and they'll show you you can actually run a version of Lean in your browser, and there are all kinds of textbooks, and you can go to YouTube videos and recordings. So the materials are out there if you want to start, if you want to experiment for yourselves. But let me tell you a little bit more about about interactive theorem proving. Okay, so yeah, so here is an outline of the talk. So I've already, given you a general sense of interactive theorem proving. So now let me talk about why interactive theorem proving might be of interest to mathematicians, so why mathematicians should care about it, why logicians should care, and then why philosophers should care. I mean, these categories aren't mutually exclusive, so you can be a mathematician and a logician and a philosopher. But I'm going to give you three perspectives on why the field is interesting. And then at the end, I'll try to tell you about some more about the lean theorem prover. So first of all, why mathematicians should care about formal mathematics and formalization? Well, in mathematics, when we do mathematics, we try to be rigorous, but we also try to, mathematics is supposed to help us understand. So we look for sort of a deep and a conceptual understanding of our mathematics. And in 1993, there was a famous article in the Bulletin of the American Mathematical Society that pointed out that there's a distinction. Sometimes mathematics is done very rigorously. Sometimes it's done in a more exploratory way where people kind of leave out the details and it's really meant to explore new concepts. And the article was made to raise this discussion about this distinction between kind of rigorous mathematics and what they called theoretical or exploratory mathematics. And they were trying to propose a way to kind of balance, the need for rigor, but also the need to let people explore. And the interesting about the thing about the article was that just about everybody hated it. Everybody, there were very angry responses or very emotional responses. So you can look for it online. In the following issue of the Bulletin of the American Math Society, they published a number of responses by mathematicians and physicists and computer scientists, all all objecting or responding to the article. But it was interesting. Sometimes the responses, even though they both disagreed, they disagreed in opposite ways. So some people said, there's no such thing as non-rigorous mathematics. If it's not rigorous, it's not mathematics. Other people said, there's too much focus on rigor, right? Mathematics is really about the ideas. And if you're too concerned with rigor, then you're putting a straitjacket, constraints on mathematics. Okay. And it reminds me that the whole debate about being rigorous or understanding reminds me of some advertisements when I was growing up. An American beer company, Miller Beer, they used to run advertisements for their light beer. So this was a beer with fewer calories. And they used to have groups of beer drinkers arguing about whether the beer tastes great or is less filling. So half there'd be a crowded bar and half the people would shout out, "It tastes great," and the other half would say, "No, it's less filling." And then somebody would get up and say, "Hey, listen, there's no need to fight. It can be both. It can taste great and less filling." So in the same way, this debate between whether rigor or understanding in mathematics is more important or one or the other, I don't think that I think it seems kind of funny to me that mathematics is rigorous and mathematics does deliver a conceptual understanding, right? We need both of them. And so I think it's interesting to think about the relationship between understanding and rigor. But in a sense, the fact that mathematical is rigorous, the fact that it's governed by very precise rules, is what makes it mathematics, right? It's what allows us to share a mathematical understanding with each other in very precise and rigorous ways. And it gives us a scaffolding. It's what we build the understanding on, and it's what makes the understanding meaningful. So in that sense, people sometimes complain about proof assistants that they're too focused on rigor and checking every last detail, and that they aren't, that they don't deliver mathematical understanding. And for that reason, I think it's better to think of as a proof assistant as a tool that can help us do mathematics better. So I think it's helpful to compare it. I like to compare it to mathematical typesetting, LaTeX. So nobody would claim that the most important thing about mathematics is typesetting, right? But nonetheless, typesetting is important. We want to be able to read our mathematics clearly. We want it to be attractive to read and easy to read. So we do recognize that it's important. And if any of you have ever used LaTeX to typeset your papers, you know that there's a learning curve. There's an effort. You have to learn the symbolism, and you get these funny error messages, and you have to respond to it. But the general feeling in the mathematics community is that it's worthwhile because even though it takes some work and investment of effort, it helps us communicate mathematics better, and so the payoff is worth it. So I think in the same way, we should view proof assistants as tools that can help us do mathematics better. You don't have to say that checking every detail formally is the most important thing about mathematics, but getting the details right is important. And so even though it takes some effort to learn to learn to use an interactive theorem prover, um, uh, in the long run, the effort should pay off. And here at the bottom, I say that interactive theorem proving is not there yet, which is to say that if I were speaking to a mathematician, I would encourage them to learn about interactive theorem proving and maybe try a proof assistant. But I can't tell them right now that it's really worth it, for their careers, because right now the technology is still very difficult to use, and it requires really a lot of effort to check your mathematics fully. So the technology is improving, but I think it's still not ready, not at the point where sort of everybody can use it, like LaTeX. Um, okay. Let me just mention one other reason why I think mathematicians might be interested in interactive theorem proving. So interactive theorem proving in general is one instance of what are known as formal methods in computer science. And by formal methods, what I mean is just a body of logic-based computational tools that are used for specifying, developing, and verifying hardware and software systems. And so the reason that they're called formal methods is that, so first of all, they rely on having formal languages, right? So you have precise syntax and grammars to make claims, to state claims, and express constraints. Um, they rely on formal semantics, right? So that says what your assertions mean or what it means to satisfy some constraints. And then there are formal rules of inference that, for example, you can use to verify that a claim is true, or to search for something and know that that the steps you carry out in the search either preserve soundness or preserve completeness, um, so that you know when you found the thing that you're looking for at the end. Okay. So this is what that they're used for verifying hardware and software. But if you think about it, mathematicians need to make assertions, and their assertions have a meaning, and they search for results. And so it's not surprising that the same methods used in computer science can be used in mathematics, and they can be used to verify proof, the correctness of proof, and verify the correctness of mathematical computations. But also to search for mathematical results. So to search for mathematical objects and mathematical proofs. And moreover, they give you tools that you can use to store mathematical knowledge, to share, to communicate it, and to search it, to archive it, to find it in databases, and so on. And so I like to think of interactive theorem proving as, well, here at the bottom, I describe it as a gateway to formal methods. It's just one component. So once you have mathematics formalized, you can then use it, again, you can not only verify correctness, but you can use it to search for new results and communicate and share as well. Okay, so this is my overview of why mathematicians should be interested um, in interactive theorem proving. So far, so good. Any questions or comments? So in the chat, I should say that I have another monitor here with the chat window open, so I can read questions there. So I see a question from Yunbao Shi. It's a technical question. So LaTeX can be built on Visual Studio Code. So is there any proof assistant can be done so too? And yeah, so in fact, later I may in fact give you a little Lean demo. But right now, Lean, there are two editors that support Lean. One is Emacs, and then more commonly is Visual Studio Code. And the Visual Studio Code, the editor mode for Lean is quite nice. Is equal to 0, then it returns 0. Otherwise, if A is a square modulo P, then it returns 1, else -1. And the law of quadratic reciprocity says that, well, if P and Q are distinct odd primes, then the Legendre symbol of P and Q times the Legendre symbol of Q and P is -1 to the P over 2 times Q over 2. So here this is P modulo 2. So saying that P modulo 2 is equal to 1, that's just the idiom in lean. This is how we say that P is odd. And similarly, that Q is odd. Okay. So if P and Q are odd and distinct, then the Legendre symbol of P and Q times the Legendre symbol of Q and P is equal to -1 to the P over 2 over times Q over 2. Similarly, here's an example of Celo's theorem. Here, G is a finite group. P is a natural number that's a prime. This theorem says that if P to the n divides the cardinality of G, then there is a subgroup of G whose cardinality is P to the n. Okay, so this is a part of the Celo theorems. Okay, so again, if P is prime and P to the n divides the cardinality of the group, then there's a subgroup of cardinality P to the n. Just some more examples, if you like, category theory. Here's a development of category theory in the Lean library. Scott Morrison is one of the authors who's been developing category theory. So again, I won't. I mean, this is just a definition of the Yoneda embedding, and I won't try to sort it out. But the theorem is that the Yoneda embedding is full and faithful, so that can be expressed in Lean. And here, just to show you, that you can actually get, fairly complex mathematics. So Sebastian Guzel does ergodic theory in France, and he's formalized a library for manifolds. So here's his definition of a smooth manifold with corners. And again, I can't make sense of the whole thing, but I just want to point out that there are a lot of parts. So you need so here K is a normed field. E is a normed space over K. H is a topological space. Then there's something he's defined, which is a model with corners. There's something he's defined called a charted space. And smooth manifold corners has all those data, and then something is a groupoid. So I don't know what it all means. But the point is, you can actually put together very complicated algebraic structures with an interactive theorem prover. And dependent type theory, this is one of the advantages of dependent type theory. Dependent type theory is good for reasoning about algebraic structures. Okay, so I think I've just 2 more slides to talk about why logicians should care, and then again I'll pause and see if there are any questions. So if you're interested in logical foundations, that's one reason that a logician might be interested in interactive theorem proving. But another thing is automated reasoning, and I think it's a very exciting time for automated reasoning right now, because in a way the field has gotten mature. We understand the basics, but in a way things are just starting to happen. We still have a lot to learn. So when it comes to automated reasoning methods, the idea is when you're formalizing mathematics, it's very tedious to write down every detail. So as much as possible, you would like to have the computer help you formalize mathematics by filling in details. And Bohua, I know, has done some very, very good work along these lines in Isabelle. So he's designed automated reasoning methods that will help construct proofs in Isabelle. But so when it comes to automated reasoning, there's a wide, it's really kind of a vast landscape. People sometimes distinguish between domain general methods and domain specific methods. So domain general methods, these are tools that are supposed to work really just across a very wide range of contexts. And so, there's propositional theorem proving, first order theorem proving, higher order theorem proving. There are systems that focus on equational reasoning. And then there's a body of tools called combination methods, which are really good. They're kind of frameworks for combining different styles of reasoning. Okay. In particular, they're very good for combining domain general reasoning with domain specific reasoning. And by domain specific reasoning, I mean automated reasoning tools that do more restricted things, but do it very well. So for example, there are systems that deal with integer linear arithmetic or real linear arithmetic. And so, there are systems out there, that can solve systems of linear real constraints with, hundreds of thousands of constraints and tens of thousands of variables, right? So there's very, very complex, automation can do very, very complicated things. But the trade-off is it's just linear arithmetic. So it's just things like 3x plus 2y minus 5z is less than 7. Imagine just lots and lots of inequalities of that form. So very restricted forms. There are systems that do better with that can do nonlinear arithmetic. So polynomials and possibly even more complicated transcendental functions and so on. And then there are a body of tools that are based on algebraic methods. So so there's a lot going on in automated reasoning, again, for logicians to learn about. And again, what I like about interactive theorem proving is that it's where theory and practice come together, right? So if you look at 20th century logic, it's about formal languages and, in principle, what formal languages can do. And now the focus is on, well, what are good languages to use if you really want to write down mathematics and formalize it? Again, 20th century logic was about foundations and in principle, what they can do, and in principle, what the right foundations are. And now we're asking, well, in practice, what are the foundations that we want to use to prove theorems? And similarly for decision procedures, instead of decidability in principle, you want to know what your systems can actually do. And so, we need to understand how to manage large databases of mathematical knowledge, how to find things in the database efficiently, how to combine different methods of reasoning automatically. Tools need to learn how to use external automated reasoning tools and then interpret the results. So there's kind of communication problems, translating problems between representations that different systems can understand. We need to understand how to use computer algebra systems and use them in a way that we can actually have very precise semantics and precise guarantees that results are correct. We need better ways of sharing data between proof systems. We need better ways of verifying computation, both symbolic computation and numeric computation. And then for all us logicians, we're all of us are looking at machine learning with a little bit of anxiety, right? Machine learning seems to be taking over the world. And there are some very impressive things in recent years that machine learning can do. But it still seems that there are some things where symbolic methods are really more appropriate. And so, the important questions are, what are the things that are appropriate for symbolic reasoning? What are the things that are important for machine learning? And, how do we distinguish between them? Okay. And so finally, let me say that, so what I like, as I said, what I like about this is that we're doing logic, but we're thinking about applications. And really, to make it work, we really need to pay attention to the mathematics that we're modeling. So what I like about interactive theorem proving is that you have to look very, very closely at what mathematicians say and what they do and their reasoning patterns, and you have to understand how to model them. And I think that's very, very attractive from a logical point of view. Okay, so let me pause again now and give you a chance maybe to ask some questions. It's also good for me. It gives me a chance to have a sip of water. Okay, so if there are no questions, again, feel free to interrupt any time. But now let me say something about why philosophers might be interested, because I understand that in Wuhan the logic is housed in a philosophy department, and so now let me focus on the philosophical perspective for a couple of slides. So developments in formal methods, they raise interesting philosophical questions, I think. So most philosophy of mathematics in the 20th century has largely focused on questions of justification and correctness. What justify where do the logical rules come from? So the focus has been really on these things, and of course, interactive theorem proving fits in naturally with these topics, but it gives a new perspective. I mean, so the questions, how do we come to have reliable mathematical knowledge? To have reliable mathematical knowledge. I mean, ordinary mathematical proofs are much too complex to write out formal axiomatic proofs by hand. And so interactive theorem proving gives us a way of understanding how you can build up more complex, robust mathematical knowledge from these very low-level primitives. Okay. And so it gives us a better understanding of the means, the mechanisms that we can use to recognize the correctness of a complex mathematical proof. And also raises questions, can we and should we trust proofs that have computer-generated components? So as time goes on, we're beginning to see computers used even in pure mathematics in more substantial ways. And the question is, well, one question one can ask is, can we trust those results? Does that qualify as mathematical proof? And these are fundamentally epistemological questions. These are questions about mathematical knowledge. So I think that puts it firmly in the realm of philosophy. But more interesting than questions of justification and correctness, I think, are questions of mathematical understanding. So this is a topic that's of greater interest to me, and I think to mathematicians as well. So I talked about the Jaffe-Quinn debates and the concern about rigor and understanding. Yes, mathematicians are concerned about rigor and what makes a proof rigorous, but they don't worry about it as much. I think, in their day-to-day lives, they're much more concerned with how do we get a proper mathematical understanding? What is the nature of a mathematical understanding? And so I think interactive theorem proving can also help in that regard by giving insight into how mathematical language and methods support understanding. So for example, when you model complex algebraic structures in an interactive theorem prover, you come to understand how algebraic structures package information, how they make some information salient, how they hide other information, how they kind of manage and control information in useful ways. And so I think just by modeling mathematics formally, you get a better insight as to how it works and how it supports our understanding. Okay. Going the other way around, using computers and proofs also raises interesting question as to what kind of understanding we're after. So for example, when you can reduce a proof to a longer computation, it may be that the computation is just too long for you to carry out by hand. So humans cannot check the result of the computation. But nonetheless, I think we're coming to realize that sometimes a calculation or sometimes just a brute force enumeration is all that we can expect from, in a proof of a theorem, and maybe it's all we want, right? So some theorems seem to be of the form that, that the way to, the only way to prove them is to reduce them to a long calculation, and then you do that. So I think that's sort of getting us to think about what we want from mathematics. Case maybe where the understanding goes is understanding how to reduce mathematical problems to the kind of enumeration. Okay, so I think formal methods again raise interesting philosophical questions about the nature of mathematical understanding. And what we're looking for in mathematics, yeah, and what we value. Okay, and so okay, so I've sort of making good time. So there will be time for discussion and for me to give you a little at the end. So I've told you about interactive theorem proving. I've given you sort of a big picture of what the practice is, and I've tried to tell you. So now, if I may, I'd like to tell you about Lean, the particular theorem prover that I've been working with for the last few years. So Lean is a relatively new interactive theorem prover. It was developed by, so the principal developer is Leonardo de Mora, who is a researcher at Microsoft Research in Redmond. And Leo is one of my heroes. He's really one of the most remarkable people I've ever known. He's just a He is a remarkably good programmer. He has tremendous amounts of energy, but he has this amazing ability to go into any domain, find out what the problems are, and just kind of throw himself into it, just find the perfect, elegant solutions, and really just find and then implement them and then get them to work. So he's very much a perfectionist, and he's really given us an amazing gift with Lean. So the theorem prover, it's open source, which means that anybody can use Lean any way they want, market it, sell it, make money off of it in any way that they want. So it's a very permissive license. So the project was launched in 2013. And then in around 2017, Leo found that so a number of people were starting to use Lean and get excited about it while it was still under development. There was kind of a stress point where Leo began to be overwhelmed that so many people were using Lean in their requests for various things. And so the solution was in 2017, there was kind of a division where people using Lean, they split off the library from the core development, and the community took over the development of the library. And meanwhile, Leo began, working on Lean 4. And since then, the community has been maintaining the Lean 3 and then building the library around that. So there are now two versions of Lean. There's kind of the one that's in current use, which is maintained, developed by the community, and there's a library around it. And then Lean 4 is still under development. And I'll say a little bit more about the differences between them. But we're looking ahead. It will be painful to kind of port the libraries from Lean 3 to Lean 4. So this is something that we're looking ahead to. So there will be some pain points ahead. But Lean 4 is shaping up to be a really remarkable system. And so we're all excited about it. It will be well worth it. Okay. And as I said, when you go to the Lean community web pages, there's a lot of information there. So what do I like about Lean? So first of all, of the various foundations, so the set theory, simple type theory, and dependent type theory. So it's based on a dependent type theory, which again, there has advantages and disadvantages. Some people like set theory, some people like simple type theory, some people like dependent type theory. There are differences between them, there are advantages. Dependent type theory is good for algebraic reasoning, which I think is really essential for lots of parts of mathematics. It has a small trusted kernel and independent checkers, which is to say the part of the program that is actually checking the correctness of the axiomatic rules, as far as dependent type theory goes, is fairly small. So they're a very small trusted part of the code. So let me say that dependent type theory is more complicated to implement than simple type theory or set theory. So it's a more complicated axiomatic system. But as far as dependent type theory goes, Lean's implementation is very clean and very small. The syntax of interacting with the system is very nice. As I said, there are mechanisms for dealing with algebraic structures that are good. It has a very nice editor interface. Well, it has a couple of them, but specifically VS Code. There's also a version of Lean that you can run in your browser with no installation at all, which is kind of nice just for playing around with it and trying it out. So one thing that's been nice, Lean 3, the third version of Lean, first introduced a metaprogramming language, which is a language in the system itself that you can use to write automation for the system. So in other words, you have a theorem proving language, a language for writing mathematical statements and mathematical assertions and mathematical proofs. And roughly that same language can be used also to write automated reasoning procedures. And so that's really, and there's a philosophical message there. It says when you're building a mathematical library, the mathematical library isn't just theorems and proofs, definitions, theorems, and proofs, but it's also procedures, right? Having a library of expertise, mathematical knowledge, isn't just facts, but also procedures for calculating, for reasoning, and so on. So the Lean library has both theorems and definitions and so on, but also reasoning procedures that extend the functionality. But Lean, so there's good documentation, there are a number of tutorials for Lean. And so this is talking mostly about Lean 3. And then Lean 4, the difference between Lean 3 and Lean 4 is Lean 3 is designed as an interactive theorem prover that just so happens to have a little bit of a programming language built in. Lean 4, in contrast, is designed as a programming language, and a programming language that is so expressive that if you want, you can also use it as an interactive theorem prover. And so that's really exciting. One effect of that is that Lean 4 is very, very configurable and extensible. So the reason that Leo is implementing it this way, so as I said, with Lean 3, he was sort of overwhelmed with people making requests for reasoning procedures and syntactic extensions and so on. The thing about Lean 4 is that because it's more like a programming language, users will be able to do whatever they want. If they want to extend the syntax, they'll be able to. If they want to add automation, they'll be able to. Right. So evidence that that Lean 4 is a good programming language is that it's written in itself. So it's implemented in Lean 4, which sounds circular, but logicians should like that. So most of Lean 4 is written in Lean itself. Yeah, so it's shaping up to be a really remarkable system. But just about my favorite thing about Lean is the community. So the people involved they're enthusiastic, they're energetic, and they're welcoming. It's really a great bunch of people. So as I said, the community's been developing the library, which is called MathLib. Been called that since the beginning. It recently passed 500,000 lines, which is pretty big. It's not the biggest. I mean, Isabel's library is substantially bigger. I think the library that ships with the system is like 1 million lines of code, but then there's an archive of formal proof, which I think is close to 3 million. So there's systems out there that are bigger. But then again, Isabel has been around since the 1980s, and Lean the system has been around since 2013, and it's really MathLib has only been around since 2017, so it's really grown a lot, and it's growing very quickly. There's a Lean Zulip chat. Let me see if I can show you that in my browser. Let's see. Yeah, so if you kind of go, there's kind of a social media chat group that if you go, I try to keep up every day, but if you kind of look, this is 4:30, 4:07, 4:45. Throughout the day, people get on and they wake up in the morning and they turn on their computer and they start working on Lean. And people ask questions. There are people who have been around for a very long time. There are newcomers to the system. It's very welcoming, but people ask questions, and so it's a great way that you're kind of never working alone if you're with Lean. You can always, if you have any question, you can kind of just go to go to Zulip and ask a question, and often questions are answered in just a few seconds. So it's a very tight-knit community. As I said, the community web pages are here, and again, you can get documentation. So there's information on textbooks and online textbooks that you can use. So yeah, there are lots and lots of resources out there. So one thing that I think is special about Lean is that it's really the first theorem prover that has captured the attention of the mathematical community substantially. In 2017, I could say that the number of mathematicians using interactive proof systems, it was a very, very small number. I mean, there were a few in Isabel and a few using Coq. And by that, I mean, I don't count logicians. I mean, just mathematicians. Logicians were playing around with these systems because they were interested in the logic. But there are very few mathematicians interested in it just for doing mathematics. And now in Lean, there's a very, very lively and active mathematical community, ranging from, number theory, algebraic topology, dynamical systems, topology. And these are really quite good mathematicians who are excited about formalizing mathematics in Lean. So it's really, attracted the interest of a good mathematical community, which is nice and exciting. And because it's research mathematicians, there's an emphasis on not just formalizing theorems that have been around for a long time, But there's an emphasis on trying to formalize things that mathematicians are currently interested in. So, for example, Sander Dahmen, Johannes Holzel, and Rob Lewis formalized or proved the Ellenberg-Gieswicht theorem. So this is a theorem that appeared in the Annals of Mathematics in 2017. And so the Annals is one of the foremost mathematical journals. So this is a combinatorial theorem. They were very careful to, they went out of their way to try to choose a recent theorem that was kind of small and self-contained enough that they could formalize it in a proof assistant. So, most papers published in the Annals of Mathematics today are just too far out of reach because they just require too much background. The proofs are too high level. So they were very careful. They're very strategic in choosing a recent theorem. But the point is that it was a theorem that mathematicians are still talking about and interested in. So it was a kind of a landmark to formalize something very recent. Similarly, a few years ago, Kevin Buzzard, Johan Komelin, and Patrick Masseau formalized the notion of a perfectoid space. So really not even much by way of theorems, but even just the definition of a perfectoid space. So perfectoid spaces were developed by Peter Schultz, a recent Fields medalist. And so again, their interest was formalizing something that was very much of contemporary interest. And so Patrick is very good at making sort of nice web pages. So you can go and read about the project Perfectoid Spaces and see the definition, explanations about the code and so on. And then yeah, I mean, Patrick is also good at getting kind of visual displays. So yeah, I mean, I don't know how he generated this, but this is just kind of some schematic picture of the different topics that are formalized and how they relate to each other. So yeah, so that's the Perfectoid Space project, and along those same lines, so Komelin, Johan Komelin is leading a number of research to do a formalization that was issued by Peter Schultz, so the liquid tensor experiment. Then piece that he said, I'd really like to see this theorem formalized, and Johan and others took a look at it and decided that it is within reach, and so now there's a project to formalize this. Okay, so the point is that Lean, we're sort of getting we're sort of getting close to contemporary mathematics. Okay, so I've been talking for a little bit more than an hour, but the good news is I am almost done. So let's see. So I've told you about interactive theorem proving. I've talked about why mathematicians should care about it, why logicians should care about it, and why philosophers should care. I've already showed you a lot of these things. The Lean community web pages, the web editor, books. So the nice thing about, let's see if the textbooks for Lean is that they're built in this way. You can read them in HTML, but all of them are, if you click on the boxes, it opens up a sort of a live Lean browser. So this is Lean running here. And the browser version, the first time you load it, it takes a little while for it to load, but it's actually running in your browser, and you can type things. And I mean, I'll show you this in another window, but you can sort of type commands and get feedback from Lean. So yeah, I mean, you don't even have to install anything. You can go right now to the documentation, click on things, and just start playing with Lean. But again, I'll pause and give you a minute or two to see if there are any questions. But then, if you'd like, I can then show you what it's like to interact with Lean. So I can open up VS Code. So I actually have it open somewhere. So I can open VS Code and just start typing things into Lean and give you a better sense of what the interaction is like. So, but because I've been talking for a while, so before I do that, let me pause and ask: are there any questions or comments or anything else you'd like me to talk about?
I have a question. Is that all right?
Yeah, please.
Yeah, I mean, in your last section, you were you mentioned a couple of the the theorem provers based on type theory and set theory. At the beginning of your talk, though, you also mentioned ACL2, which is
Yes.
based on a subsystem of second order arithmetic, right?
No, so ACL2 is actually kind of an interesting
Oh,
system. So
sorry.
this one here you're talking about, right?
Yeah,
ACL2?
yeah.
Yeah, so it's actually it's written in Lisp and it's very close to Lisp. So you're
Okay.
really kind of so ACL2 stands for a computational logic, I think. It's based it's a later incarnation of what used to be called the Boyer-Moore theorem prover. So Bob Boyer and J. Struther Moore at the University of Texas at Austin developed it. If you had to describe it in axiomatic terms, it's pretty close to primitive recursive arithmetic, which is really fairly weak. In the sense that it's really just about writing explicit computational functions and reasoning about them explicitly. Since then, there's some additions to ACL2 that take the strength up to first order arithmetic. But compared to all these other systems, the logic is fairly weak. But the reason it's weak is that it's really meant for reasoning about things that are very explicit and very computational. ACL2 is also used to reason about, so it's AMD uses ACL2 to verify properties of processors and so on. So it's used to verify, fairly computational applications.
Yeah, so that was going to be my question. Is there a sense that that a proof verified in something like ACL2, which has a much weaker background logic, is worth more than a proof verified in one of these other systems? Or?
Yeah, so there, I think, so logicians really care about logical strength and so on. I think, to mathematicians, if it's set theory, I trust set theory, and that's it. So simple type theory is a little bit weaker than set theory. So if you take Zermelo set theory, so you throw out replacement, then you're just a little bit stronger than simple type theory. So simple type theory is in terms of strength, it's like Zermelo set theory with only bounded comprehension.
Yeah.
Yeah. Okay. So it's just like finite iterations of the power set operation. So the basis for Coq and Lean, if you're using it classically, the strength is a little bit stronger than Zermelo-Frankel set theory. It's Zermelo-Frankel set theory with countable sequence of universes, so Tarski Grothendieck universes. So it's a little bit stronger. And if you want, maybe later I can say a little bit more about what these universes do for you. I mean, they're just, it's basically for quantifying over large things, right? So you want to have, you want to quantify over groups. You want to have a big universe of groups. So you want to quantify over all groups in the universe. But roughly, yeah, so so most systems are either a little bit weaker than set theory or a little bit stronger than set theory. Yeah, I don't think mathematicians worry too much about the, I mean, again, logicians like to know how weak a system can you get away with. Practically speaking, I think the more important question to mathematicians is, can I formalize the mathematics I want to formalize, and how easy or hard is it to do that? And so it's really more the expressiveness of the language and the expressiveness of the system and so on. That's really the deciding factor.
Cool. Thank you very much. Thanks.
Yeah, very welcome. And so I see another question in the chat from Yanjing Wang. Could you say a bit more about how using Lean and other theorem provers can give us a better mathematical understanding? E.g., can formalizing the Ellenberg-Gishovich theorem in Lean help people to understand better the idea behind its proof, not just verifying the proof? And so that is a very good question, and it's not easy to answer in short terms. So so remember I said with the Jaffe Quinn articles, a lot of people, complained that, well, when you formalize mathematics, that's where the mathematics just dies, right? There's understanding, and then the formalization is just the symbolic pushing, Once you get to the point where you understand the idea, then it's just a calculation, just filling in details. So a lot of people feel that there's a tension between formalization and understanding. That said, sometimes when you do go to formalize mathematics, because it takes such an effort, you find that what you have to do is kind of reorganize the mathematics and fit the pieces together. To get the pieces to fit together in the right way, you really have to think about the concepts and how they interact. And that often leads you to reorganize the mathematics and then understand it better. So let me just give you um, two examples that come to mind. So one is the formalization of the four-color theorem in Koch. So to do that, Georges Gontier, so the idea is you have to reason about planar, I mean, it's about planar graphs. And so you have to reason about planar graphs or graphs that can be embedded in the plane. And so to formalize it, Gontier used a combinatorial structure. He wasn't the first, but he sort of put it to very good use. It's a structure called a hypermap. So a hypermap is a certain combinatorial representation of a planar graph where you have the faces and the edges and the cycles and so on. And it was, he developed this conceptual structure just because it made the formalization easier. But I think combinatorists have sort of picked up on this. And for a lot of things in discrete mathematics, it turns out that this is a very nice structure, a nice representation of the data, of the mathematical knowledge. Let me think. I mean, Tom Hales also has talked about in formalizing the Kepler conjecture that that caused a lot of reworking that led to sort of a better understanding of the material. But one more example I want to mention is, so in Isabel's library, as in Lean's library, there's this issue of when you formalize analysis, you find that you have to formalize the notion of a limit. The limit as x approaches 5 of, x squared plus 7. Right? And the problem with formalizing limits is that there are too many variations, right? So when you talk about the limit as x approaches, x can approach some number, it can approach infinity, it can approach negative infinity. You also might have x approach some value from the left, it might approach some value from the right. And then if you look at the output values, as x approaches 5, f of x can approach some number like 7, it can approach infinity, it can approach negative infinity. And so if you just start to formalize the notion of, develop a mathematical library for limits, naively, you find yourself just duplicating definitions and proving the same things over and over again. And so a few years ago, so I guess there are a few different people who hit upon the idea independently, but one strand was Brian Huffman and Johannes Holzel, I think one other co-author in Isabel, developed a very nice library for limits based on the notion of a filter. And Brian Huffman came to it from domain theory in computer science to develop this notion of a filter. But it turns out that the idea goes back to Bourbaki. If you go back to Bourbaki, and the notion of a limit is based on this abstraction known as a filter. And all the mathematicians I know of working with Lean just really love this notion because it's just an elegant conceptual notion. It's just sort of the right way to think about limits abstractly. And so that's another situation where developing a formal library leads you to think about the concepts that in a way that gives you a better understanding of the mathematics. To mention another example, Patrick Massot has given nice talks about formalizing, again, material that in Bourbaki, but realizing that, initially he wrote down, he was reasoning about topological spaces and subspaces and so on. And he had one theorem, he was formalizing something in Bourbaki and realizing that the proof wasn't quite right, but found that instead of dealing with spaces and subspaces, instead if you deal with a space and an injection, right? So just kind of a structural, using mapping properties. And it turns out that there are lots of things that just the formalization becomes much nicer when you just take the right abstract kind of conceptual structural perspective. So there are lots of things that are conventionally, cast in set theoretic language and so on, but with the right algebraic abstract perspective, the formalization becomes easier. But in finding the right formalization, I think people feel like you're getting a really nice mathematical perspective and understanding as well. So those are examples where the process of formalization, I think, gives you a better understanding of the mathematics. But the other thing that I'd like to mention is I think when you look at what it takes to implement the language, when you look at the specifics of proof languages and what you have to do to make them work and how you represent algebraic structures and what kinds of things you have to do to reason about structures. As a logician, what I like about that is I think that gives you a really nice perspective on mathematics. It helps you understand, well, again, how mathematical language works and how mathematical inference works. Part of it is, when we read a mathematical text, with mathematical training, there are lots of details that we can fill in automatically, things that we don't have to think about at all. And then when you look at how hard it is to implement this by computer, you realize all the things that mathematics is doing for you, right? Just by having certain ways of arranging information, right? Certain things become automatic. And so, again, the very act of implementing and formalizing gives you, I think, some interesting insights as to what makes mathematical language so powerful and how it works to support our inferences. Okay. Oh, another question in the chat. So let's see. So from Yumu Kompaku, and again, I apologize if I'm butchering, if I'm mispronouncing your name. But so the question is, are there any general settings about formalizing metamathematics and proof theory in Lean, or any other ITPs? Moreover, the foundations of ITP is bootstrappable. And yeah, so there are a lot of questions. MLTT, Pfefferman's FM0, strong axiom. Let me just give a broad answer. And so yes, the answer is absolutely, certainly. You can formalize anything. You can formalize number theory and topology and analysis